So in this video I'm going to show you how to make these procedural caterpillars using geometry nodes in Blender 3.4. It's quite a long video, but there's a lot of work to get through, so let's get started. Okay, let's get this scene set up. We don't need the default camera or light, you can get rid of them. We'll leave the cube so that we've got an object to host our geometry nodes tree. And we are going to want a path for our caterpillar to walk along. For that, a simple Bezier will do for now, and we are also going to need a surface for the caterpillar to conform to. Plane will work fine. I'm going to give it a little bit more size. Quite a few subdivisions, so we've got a good amount of geometry to work with. I'm going to apply that subdivision, go into edit mode, and with proportional editing turned on, like that, just so that we're not working with a completely flat surface. Okay, let's go into a geometry nodes layout. Let's add a new tree to the cube object. We can sever this connection because we don't need to see that cube anymore. So what we want is, we have a path for the caterpillar to walk along. I'm actually going to make this path a little bit bigger as well. I'm going to raise that up above the surface slightly, just so that we can see it more easily. And what we want to do is create a smaller curve that's going to make its way along the points of this curve whilst also conforming to the surface of this plane. We'll do a simple curve line, and we want the ability to control the length of our caterpillar, so I'm going to do a combine XYZ. I'm going to take the Y and create a new input. Call this one length, maybe 0.5, minimum 0, maybe 3 should be enough. And this vector is going to be the end of our curve line. So if we actually give this a value for its length, we should see we have a little line segment going along the y-axis there, 0.5 meters. First of all, let's give our line some extra geometry to work with. We're going to resample. And we're also going to want to control the number of segments of our caterpillar, so we may as well expose this as a parameter as well. Call it segments. So we're going to need to have access to our path. Let's expose that again to the outside so that we can choose our path from the modifier panel, and we're going to sample positions on this curve. And because we're dealing with a known length for our caterpillar, we're going to sample by length rather than factor here. And because we've set the length of our initial caterpillar curve to already be the length we want, we can use its Y position to determine the length along our path that we want to sample from. So we drop down a position node, separate the vector, and we're interested in its Y position, and then we set the position of our points. Let's hide our path for a second, and there we can see our caterpillar is now popped to the position of that path. If we want to move along that path, we're going to need a time input of some description as well. So let's drop down a scene time, and what we want to do is add some amount to this sample length. For example, we could take the seconds from the scene time and add that so that when we press play, our little caterpillar now travels along that Bezier segment. I'm just going to split this panel here so that I can pop a timeline in, because we're going to need to be controlling things going back and forth through time quite a lot, so it's handy to be able to just grab that from here. So to make this a little bit easier to see what's going on, I'm just going to instance an object onto the points of our curve. So now it's easier to see. At the moment, the caterpillar is travelling quite smoothly along the path, which is not quite what we want. We want a way to have this start and stop at intervals rather than move continuously. In order to do that, we're going to take this scene time input and manipulate the seconds before we add them to our position. And there's a couple of operations we're going to need. The first one is a fraction operation, which basically is going to return the values to the right of the decimal point based on this input. So if the input was, say, 2.5 seconds, fraction is going to output just the 0.5. We're also going to need a floor operation. And what this does is it will round down to the nearest whole number. If we add these back together, we should notice no change in our caterpillar's motion. But what we can now do using a map range, and by decreasing the from maximum to say 0.5, so that should give us that stop-start motion that we're looking for. This is travelling a bit too far with each step for a caterpillar, so what we need to do is add a multiplier to something small, and then we get this little staccato movement of the caterpillar. At the moment this is very linear, it starts and stops in a very mechanical way. So what we can do here is add another map range. We're going to leave all of this at 0, 1, and all we're going to change is this from linear to smoother step. So now we get a smoother stop and start. And we could have done that just here using our original map range node, and the reason I haven't is because I want to use the output of this in a second for another operation. So we're going to keep the smoothing to its own separate node. Okay, the next step we need to do is to introduce a delay from one point to the next. At the moment all the points move at the same time. We want the movement to be initiated from the first segment and to travel along from the tail to the head. And the way we want to approach that is by adding or subtracting from the time input based on the index of our current point. So if we drop down an index node, we know we're going to need that. Our index is an integer from 0, 1, 2, 3 up to the amount of points that we've got, and that's going to be too much of a delay because we're dealing with quite small values here. So we're going to need to multiply that down somewhat. I'm going to try 0.1 to start with, and we want to subtract this value from our seconds. Bring this underneath. If we add this in, we now get this ripple effect going on, starting from the tail and finishing up at the head. Probably want slightly less of a delay. That's looking pretty good for now. These can all be exposed as parameters to be fine-tuned based on the geometry we end up using for the caterpillar. Okay, the next step is going to be to snap our path down onto the surface so that we can start to use some of the properties of this ground to affect our caterpillar. So if we bring our surface in as an object info node, we may as well expose that in the same way as we did previously. We'll call this one ground, just in case we want to swap it out for a different ground surface. And what we can do is take our geometry and do a sample nearest surface. The value that we want is position, which is obviously a vector, not a float. And we should now be able to use this output to set the positions of our original path curve. However, this original path only has a vertex at the start and the end point, so we're going to want to resample that to add more detail in order for it to be able to conform to our surface more accurately. If we resample by length, do it at 1 centimeter for now, and then if we do a set position on these points using the sampled values we just got, we should see our caterpillar snap down onto that surface quite nicely and accurately. It would also be good at this point to store the normals of this ground surface on each point of our path so that we can use that data elsewhere in our graph to displace and build various other vectors that we're going to need. Let's create a little bit more space here. If we duplicate this sample nearest surface node using our ground geometry again, this time the value we're interested in is the normal, and we will use that information in a store named attribute on our path curve. It's going to be a vector. It's going to be called path normal. And what's cool about this sample curve node is it has this extra value output, which we can specify what kind of data we want to expose from this port based on what we feed in here. So if we change this from a float to a vector and we recall that stored attribute, put this into the value, this sample curve node is now going to output the path normal for each point that we are interested in along its length. And what we can do is use that information to displace our segments vertically away from the ground as they move. So we get that nice sort of wave flowing through the caterpillar's body as it takes each step. And what we're going to do is come back to this first map range node, which has no smoothing applied to it. We're going to take the output from that into a float curve node, and we can use this to create that up and down shape. We set this middle point to 0.5, make it linear, and then we can use a map range node with default values to simply smooth that out so that we get a nice smooth curve. This is going to mean that whenever our segment is on the move, we're going to be traveling along this curve. So as we start to move, we go up. As we come to a stop, we come back down. So if we take the result of this and we use it as a scale factor for this value output, which is going to give us the surface normal, we can offset our points as well as setting their position so that as they move forward, they also perform this up and down hop. Now obviously, I think we can all agree this is a little bit extreme. Pretty energetic caterpillar, that one. So if we add another multiplier in between here, we can reduce that amount to something a bit more reasonable. That looks pretty good for now. Alright, so the basic body movement is working well enough for now. I think it's time to add some footsteps on either side of these segments, and that'll help us keep our caterpillar's feet in contact with the ground when we come to add the geometry. So first thing, I'm going to spend a moment just clearing up this graph a little bit, put some things into frames so it's all easier to look at. Okay, for the feet, what we want is to generate a set of points that's offset horizontally from our body segments. And we want those to be more or less synchronized in terms of their movement. So we can reuse quite a lot of the node setup we already have here. What we're going to do to start with is pull a connection from this initial map range, the one with no smoothing on it, and we will manipulate that slightly to give the feet movement slightly different properties. So we're going to map range this one again, and what we want to do is clamp the start and the end of its movement so that the body, as the body moves, the feet stay behind for a second, and then the feet quickly overtake the body to plant themselves down, and then they stay still again as the body catches up. And the way we can do that is to clamp the from min and from max to slightly within the 0 to 1 range, and we can use this now to drive a new set of points. So we can duplicate the curve that we're using for the body. We'll drag this guy off, and we want to set its position. We're going to need to duplicate some of this functionality that we're using on the body up here. We're going to need an add, Alt-P to unparent from the frame there, because this map range is only giving us the fraction portion of our time input, so we still need the floored seconds. We're going to need to add these back together. We need another multiplier just to keep it to a reasonable value, and we're going to need to add the Y position as we did before, Alt-P. I could just take this one, but I'm going to duplicate it just so that we can keep each area of the graph distinct. So it's the Y position we want. We're going to sample the curve again. This is the value. We want our curve, same one as before, the path. Oh, excuse me, this isn't the value, this is the length. And if we use this to set our position now, let's add a join geometry here before we instance on points, so that we can see both the curves. We should see it's in the same place as the body curve. It hasn't got the vertical displacement, it's just sticking to the ground at the moment. So what we want to do is push this off to the side, perpendicular to the body. So what we can do is we can take the cross product between the tangent of our body curve and the normal of the ground, which we stored earlier. And that will give us a vector that's perpendicular to both of those and shoots off exactly to the side of the caterpillar like we want. You can use that in the offset here to push the feet out to the side. This stored attribute, in fact, I'm going to duplicate it. Same reason as before, I want to keep this portion of the graph separate. This is going to now output the normal, so we can take that value out into a cross product operation. And we already have the tangent as part of our sample curve node, so we can push that one straight into here. And now the vector coming out of here is going to have a length of 1, which is going to push things off by a whole meter. That's more than we're going to need. So let's scale that down to 0.1 and see how that looks. Push this into the offset. And there we have our extra set of points off to the side. Now, this is probably still too much, so I'm going to reduce that slightly. So let's see if our time offset is working. Let's make this a little bit more pronounced so it's easier to see. Clamp it a bit further in. 0.4 to 0.6. There you can see the feet are lagging behind the body movement to start with, and then they're overtaking it at the other end. We're going to want to add some vertical displacement to the feet as well. So if we duplicate this portion of the graph down here, just rename it so that we know what we're dealing with. So we want to use this, same as we did before, to scale the normal vector that's coming out from this value here. And we want to add that to our sideways displacement. So now we should be pushing the points over to the side and vertically. Okay, so we're going to need to make the feet on the other side as well. Unfortunately, that requires not too much extra work, because all we really need to do is scale this cross product by the opposite, the negative version of this, and that will give us a set on the other side. So if we duplicate this one down, duplicate the add as well, duplicate the set position. And add this one into our join geometry, we get a set of feet on the other side. I actually got these two inputs the wrong way around somehow. This value is the scale, the value coming out of here is the surface normal, and that should be the vector. And now we get our points behaving properly. I think we probably want the feet to raise up a little bit less than the body. We can fine tune this all later, but I think for now this is a better look for us. So I'm just going to spend a couple of moments tidying up this section so that we don't get lost before we move on. Okay, this is a little bit easier to look at now. I did notice one mistake that I made. The vertical displacement for our feet is currently taking its input from the original map range node that drives the body, rather than this modified one that we're using to delay the feet. So this should actually be coming, the connection should be coming from here rather than the original one. I also think, just looking at this movement a little bit more closely, that these feet are sliding a little bit before they take off and after they land. And I think that is due to the smoothing that we're applying here, which smooths both ends of the curve. I think that's good for the body, but in the case of the feet, I think we should remove that smoothing and instead apply it on the curve here so that we get a linear takeoff, a smooth peak to the vertical movement, and then a linear landing. I think that will look better. So let's look at adding some actual geometry to this caterpillar model. I've brought in a collection here of body parts, which I will make available in the description for this video. So if we isolate that so we can just talk through the requirements for this model, we do have to bear one or two things in mind. We've got three objects and they are very deliberately labelled with a 0, 1, 2 at the end, so that when we instance them we can predict which order they're going to be chosen in. It's important that the centre line for each of these objects is at 0. Now I know this one is forward, but it's because it's got a y value of 1 in its position. If we reset this, the centre line will sit on the 0 axis on y. Same for the head. And the other important thing is, for this back piece, this edge of vertices need to sit on 0.5 in y, you can see there. And then for this middle section, we need negative 0.5 and 0.5. So each piece is 1 metre long. Now the head and the rear end, it doesn't matter whether these verts at the back extend further, same with the head at the front, it doesn't matter how far forward they go, as long as these pieces that need to join up with other segments are on negative 0.5. The other thing these models need, where there are feet, so it's not important for the head but for the segment and for the butt, it needs a vertex group called feet. If we have a look at weight paint mode, you can see all the value for that vertex group is concentrated down where the feet are, and you get a nice soft fall off going up into the body around that. Okay, let's look at how to add this into our geometry nodes setup and build a caterpillar. So we're going to need to drag our body parts collection into our geometry nodes tree. And what we want to do is instance these sections onto the points of our original caterpillar curve. So we're going to build the model at the origin before we do any of this moving of the points along the path. If we come back to this group is where we initially create a curve which is the length of our caterpillar and has the right number of segments. That's going to be our starting point. So if we drag a connection off there, we instance on points. And the object we want to instance is going to be the objects from our body parts collection. We're going to want to reset them so all their coordinates get reset back to 0. We want to separate the children and we're going to want to pick instance. This way we'll just get one of these objects per point. If we put that in, I'm going to attach this to a viewer node. Now at the moment these are obviously way too big, so we need a way to scale those down. So let's drop in a group input. And the scale that we want is going to be the overall length of our caterpillar divided by the number of segments we have. And because these overhang at either end, we actually need to subtract 1 from the number of segments before we divide up our length. So let's do it. Take away 1 from our number of segments, divide our length by that number, and this should give us the correct scale for our segments. Now obviously we've got a little convoy of mini caterpillars here, so we're going to deal with choosing the correct body part in a little while once we've got some of the basic movement working. So for now I'm just going to drop down a value node here so that we can choose to pick instance index number 1, which is that central body segment. So now you can see we've got a caterpillar that's got the right number of segments. We can increase this length, we can increase or decrease the number of segments, and they should always line up because we made sure those vertices sat nicely on the correct coordinate. Okay, so we're going to need to merge these vertices, which we can do using a merge by distance node. This is so we just get one seamless mesh rather than a series of separate objects. Distance can be very small, and to speed this up a little bit we're going to confine this to only consider edges with one face attached to them. Whose face count is equal to 1. And that can be our selection mask for the merge. As you can see from these orange lines, we've still actually got separate geometry here. And the reason is that before we can start to do operations on individual points, like merging, we need to realize these instances so they become actual geometry where we can access the components. So drop down and realize instances here, and now you should see those have merged together nicely along that border. Now one other thing that might be useful is now we're going to need to store some information on these points about their data before we do this process of realizing and merging. We'll probably have to come back and add a few more properties later on, but for now one thing we're definitely going to want to have access to is the segment index for each of these. So before we realize and merge them, I'm going to store a named attribute here. It's going to be an integer. It's going to be on the instance domain because at this point we still have instances. I'm going to call this segment index, and its value is just going to be simply its index. We're also going to want to store the positions of these points as they are now. So we'll do that after the merge. Another store named attribute node. This time it's going to be a vector on the point domain. I'm going to call it offset pos, and its value is going to be position. Okay, let's get this geometry conformed to our caterpillar curve. The technique we're going to use is similar to how we did some of the feather distribution in my previous tutorial about rigging a wing. If you've not seen that one, have a quick look. The link's in the description. I'm going to move a little bit quicker in this one because I don't want to explain the same concepts over and over again. We're going to need to set the position of these points. So let's drop down a set position node straight away. We're going to come down here to where we've moved the points of our body curve, and what we want to do is sample that body curve at various points according to the position of these vertices so that we can get the position relative to each point along that path. So sample curve. We want to sample by length, and the length along that curve that we want to sample is the stored Y position of each vertex. So if we recall our named attribute, called it offset pos, this is going to need to be separated. We're going to use the Y value as the length along this curve that we want to sample. If we plug that position now into here, we should see that our model has indeed moved to that curve and it's lost a bit of weight on its journey. Now we're going to reinflate this in a second, but as you can see it's moving properly along with the curve. So if we add another set position after this one, we can now use some of the properties that we stored previously to restore this back to its original volume. So we're going to treat the x and the z axis separately. We'll do the z first because that's probably going to be the easier one. So we're going to need to capture some additional info from our caterpillar curve, and one of the things we're going to need is the length along our original path that each of our caterpillar points has travelled. We set that back down here where we sample the path curve at a specific length. So we're going to store that information on the curve in here. It's going to be a float on the point domain. We're going to call it length along path. And the value of that is going to be this value here. So now when we come back up here, we can sample this curve again using the extra value input. We can specify length along path as the value that we want. It's going to be a float. And now that we know how far along our path each of our geometry vertices are, we can sample that path and ask for its ground normal, which we also stored earlier. Let's take another sample curve. The length is going to be this value that we just computed, and the curve that we want to sample this time is our original ground path, which comes from here. And what value we want is going to be from a named attribute. It's a vector. It's called path normal. It's going to be a vector that goes into value. And what we should be able to do now is use that ground normal, scale it by the z of our offset position. So we want to scale that by the z. And if we now set our position another time, using this as an offset, we should see that we get one of our axes back. So as you might have guessed, the x-axis is going to involve a cross-product operation between this normal vector that we just calculated and the tangent of our caterpillar curve. So if we take the tangent, put that through a cross-product with this one, this should now give us a vector that we can scale by the x component of our offset vector. So all we need to do now is add these two together before we put them through the, the set position, excuse me. And we get our little caterpillar back. Now there's some funky stuff going on at the ends, and this is because our first segment and our last segment actually overhang the path slightly, and you can't sample the values from a curve before or after its bounding length. But first I just want to reorganize this a little bit. I want to get rid of this viewer node and frame up this stuff. And I'm going to swap our output now so that we can just look at our final caterpillar model. Now if we bring back the ground, you can see that our caterpillar is actually half submerged, so we're going to need to offset those body points up. And now that we've got our geometry in there, we want the amount of offset to be based from that, so that if we swap the model for a different kind, it'll always be pushed up by the right amount. So if we take our caterpillar geometry here before we move it to the path, we can use the bounding box. We can take the minimum and separate that out, so that we now have access to its z component. What we're going to do is multiply the z by -1, so that will give us a positive displacement, and we can now use this as a multiplier again against the normal, the ground normal, this value here, to offset our caterpillar curve away from the ground. So we're going to need another set position node. We're going to offset the points along this value. but we're going to scale it first by this Z amount that we just calculated. And that should pop that up so that it just touches the ground. Okay, so if we look closely at what's going on here, you can see there's a bit of a problem in that as the geometry approaches the end of the curve, it's kind of collapsing down, so we're actually losing this segment. And that's because we're using the length specified by our input parameter to space these points along the curve. But in actual fact, as this curve bunches up during its walk cycle, the length of that curve is changing, so it could actually become less or more than this value that we input based on whether it's contracting or relaxing. So we just need to add a little modification back here. We're using this y value as the length that we're going to sample along a curve. So what we actually need to do is find out the true length of our curve and divide that by our input length. That will give us a multiplier for this y value. So if we take this, put it through a curve length node, drop down a group input, and we can divide true length of the curve by our input length, and we can use this to multiply our y value. And we should now see that that problem is solved. So we're no longer losing that last segment. Okay, let's look at re-establishing the overhanging portions of our caterpillar now to reinflate the tail and the head. In order to do that, we're going to need to go right back to where we brought the models in, and before we instance them on our points to create our segments, we need to store some information about this geometry. So let's take another store named attribute node, drop it in here. It's going to be a vector, and we want the position. We're going to call this one orig pos, or original position. And before we store it, we're going to want to multiply it by this scale value. And what that's going to give us is taking the center of the object as 0, it's going to give us the position relative to that for each segment individually. So if we come right back down to the end here, we can add another set position node, Alt-P to remove it from the frame. And we're going to want to apply an offset. We only want to affect certain parts of the geometry, i.e. those parts that overhang the curve. So we're going to want to set up a condition using one of our named attributes. It's a vector. This time it's going to be the offset pos. We want to separate this because we're only interested in the y component for now. We want to know whether the y component is less than 0 initially. That's going to give us all the points that are before the curve actually starts. So if they are less than 0, we're going to say yes, you qualify for this set position node. And the offset that we want to apply is going to be the tangent of the curve at 0 multiplied by this y, so by how much it overhangs. So let's go back to find our tangent. So it's going to be this one. I'm going to scale that by this y value. And if we plug that into our offset, we should get our back end of our caterpillar re-inflating. So we want to do the same for the other end. This time we want to use a different attribute. So to qualify as part of the head geometry, the y value from this offset position needs to be greater than the length that our caterpillar is specified to be. So if we take this y, do a greater than, and then we drop down a group input. So if the y is greater than length, we're going to qualify for a set position. This is going to be our selection. But this time our value for our offset isn't going to come from the offset position. It's going to come from the original position that we stored. Let's separate that as well. And we're going to want the y. Again, we're going to use it as a scalar for the curve tangent. Put this into our offset here. That should give us our head back, and it's not doing. I wonder if we're not storing that property correctly. Let's have a look. We don't want to store this on an instance domain. This needs to be on the point domain. As soon as we change that, we see our head comes back. So we should now have everything working correctly. Okay, cool. Let's swap out the first and the last segment now for the correct pieces of geometry. So at the moment we're just putting a constant into this instance index. But what we want to do is to say if it's the first point on our curve, use index 0. If it's any of the middle points, index 1. If it's the last point, index 2. So let's deal with the beginning first. You can use an endpoint selection with a start size of 1. If we say not to invert this, we should get the right piece of geometry on the first point. Now what we want to do is add 1 to this value if we're up to the last point on our curve. Let's duplicate that endpoint selection. This time we want to select 1 point at the end, and if this output's true, we want to add it to this value. And now we get the head on the last point, the butt on the first point, and body segments all the way in between. And it shouldn't matter how many segments we ask for. That should always work. So we finally have something that's starting to look like a caterpillar. The next section we need to address is the feet. As you can see at the moment, they're just sliding along with the rest of the body. They're not really doing anything in terms of ground contact. So we'll look at that next. Okay, let's just frame up these nodes that we just made to reinflate the head and the butt. And we're going to do some more position setting down at this end. So for the feet, we're going to make use of those extra offset points that we made initially. We had a body curve and we had a foot curve going down each side of that. So let's start with the set position node. We're definitely going to need that. We're going to be using some named attributes that we stored earlier. The first one is an integer. It's going to be our segment index. We're going to use that to sample specific points on our foot curve rather than an interpolated value along a curve to create a smooth sample. And the node we need for that is a sample index. This is going to be the index we want. And the geometry is going to be one of our foot curve. We're going to have to go and search for that. It's these two outputs here. So we'll take the top one first. That goes into our geometry. The type of data we want is a vector. The value we want is the position of those points. And if we put this straight into our position here, everything's going to collapse back down onto that curve. So we want to restrict which vertices are actually being moved. And this is where we're going to make use of our vertex group that we stored on our original geometry pieces. It's a float and it's called feet. We don't want to plug this straight into the selection because we want to take advantage of the fact this has some fall off associated with it. So we're actually going to put this through a mix using this as the factor. We want to mix between two vectors. The second vector being our sampled point and the first vector being that unchanged position. If we plug this in now, we should see that everything that's got a non-zero attribute for the feet vertex group is being pulled towards these points. Now the problem we've got is that even the feet on this blind side are being pulled across as well. So we're going to want to remove those from this mix. And the way we can do that is to look at their original position. So another named attribute, original position. So we'll separate that. And we want to check whether its x component is greater than 0. If it is, i.e. it's coming out this way, we want to remove it from this selection. So we're going to subtract this value from our feet attribute and use that instead. And you should see these guys pop back to where they were before, whereas these ones are nicely being sucked in towards those points. Now we need to duplicate this little setup, but using the curve on the other side. And this time we want our selection to check whether or not the x component of our original position is less than 0. So now we have our feet sticking to the ground. And what we need to do next is to just reinflate the guys that have been affected by that operation back to their original volume. And we'll start with the y-axis, which is going to be the easiest one. Make some space. So we're going to need to sample our curve once more. This time, instead of position, we're interested in the tangent. that goes into here. We can scale the tangent using our orig position y, and we can scale that once again by our feet attribute. We should get back our first axis. Let's just organise this a little bit. Now for the z, vertical axis, we want to sample the normals of our ground at the exact point of the foot contact. So we do a sample nearest surface. It's a vector that we're interested in. It's the normal. And we're going to need to go and find our ground way back here somewhere. So same deal, we're going to scale this by our z original position and scale it again by our feet attribute. Let's add these two vectors together, and that should give us back our z. And the reason it's not is because in our original geometry, the 0 point wasn't at the bottom of the feet, it was through the centre of the body. So we're going to have to correct this by the minimum bounding box value on the z-axis. It's the same value that we used to offset our caterpillar curve way back here. So before our first scale operation, we want to add this in, and that should pop them back to the right place. Okay, so that's two of our axes done. We just need to do the x now, which will involve our old friend, the cross product. So we want to cross this tangent sample with this normal sample. Scale this one by x of our original position. And I'm actually thinking we don't need these second scales necessarily, because we can scale the whole thing by feet once we've added them all together. Let's add our x in, and now let's scale the whole vector by our feet attribute. And there we go, that's one side done. Now it looks a little bit distorted here, and this is probably just because where we made our footstep curves, these offset values will need to be tweaked based on the model that we're using, so we probably want to offset this a little bit less. That looks about right. Before we do go and duplicate these nodes over to the other side, we need to take care of one more little thing. If we look at this offset, it's affecting both sides. We handled that for our initial set position, but we haven't handled it yet for the offset. So we're going to need to add a mix node in here as well. It's a vector. We want to mix between the offset we just computed and a 0 offset. And we want to use our comparison here, our x check, as the mix factor. So now we're only affecting the side that we're working on. So if we now duplicate all of these using Control-Shift-D to maintain the connections, it should just be a case of connecting up the correct curve to these two samples. I'm going to swap this to less than, so it's now checking for verts on the other side, and then connect up the result of this to our position and this one to our offset. So I'm guessing this is just the fact that we haven't sorted out our actual offset where we made the points. We changed this one but not this one, so make those equal and then we should be good. So we're just about there, and we're on to the sort of nice to have features now. The first one I think we should look at is a little bit of squash and stretch, so that as this curve compresses, we get a little bulge that travels along the caterpillar's body. So this area of our graph here is where we move the body to the path. So let's make a bit of space in there in order to do our squash and stretch. So this scale here is our x, or our width of our caterpillar. So if we were to add a multiply node here, we can set this to 1, we get no effect. If we change this multiplier, we can make our caterpillar thicker and thinner on our x-axis. And this is where we're going to grab the vertical displacement. So in order to access that information on our geometry, we're going to need to store the vertical displacement on our curve here. So if we do another store named attribute, it's going to be a float. We'll call it vertical displacement, and we want the value to be in this 0 to 1 range, so we won't take the multiplied value, we'll take the actual map range output. So then when we come back to our graph here, we can sample the curve again, and this time we want the value to be our new named attribute that we just made. Change this to float, and this will be the multiplier, but we want to add 1 to it by default, so that we always have a scale of 1 as our baseline. Nothing should change until the caterpillar starts to raise up. And for some reason we're not seeing any bulge. Have I got the right curve plugged in? No. Okay, we need this curve, our actual caterpillar curve, not the main path that the thing was travelling along. So as soon as we have that, you can see now as it raises up, it gets wider. Now we can add exactly the same multiplier to our Z component, and we will get the height as well. Now this is obviously a bit too much, so we're going to need one more multiply in between here, which we'll probably want a control over on our group input. So we'll call this one squish, and let's set this down a little bit. And I've just realised another mistake. You see how it's kind of bulging uniformly along the length, not just the area where it's raised up. That's because not only did I have the wrong curve plugged in, I actually had the wrong value going into the length as well. We want to steal this value instead. And now we just get the bulge on the areas that are raised up. They're looking quite nice and organic, I think. So there's just one more thing that I think really brings this caterpillar to life, and that is to have its head gazing about from side to side as it crawls rather than just staring straight ahead. So we're going to add another little section before we put the feet on the ground. Let's start by sampling our caterpillar curve again. We'll leave it on factor this time and sample it at 90% along the curve. We're going to use that position in a rotate vector node, vector rotate. The position's going to be the center of where we want the rotation to happen. We're going to use the value slot to extract the length along the path attribute that we've stored. And we're going to use the value that results in this to sample our main path curve, which we'll need to go and find. We're not actually using this as the value. We're going to change this to length and use this to sample at a given length. And the value that we want is a vector, and it's our named attribute path normal. This is going to give us the normal of the ground at 90% along our caterpillar curve, which we can use as the axis for our rotation. And the angle, let's just give this some value. We need to provide a vector of our current position of our points, so we know where we're rotating from, and then we can add another set position node and hook this in. As you can see, we're now rotating around that 90% point on the curve. Now obviously we want to limit this rotation only to this front end of the caterpillar, and to do that we're going to recall yet another named attribute. It's going to be a vector. It's going to be the offset pos. We're going to separate it, and it's the Y that we're interested in. That's going to go into a map range, and we want a group input so that we can put our specified caterpillar length into the from max. We want the from min to be 90% of our length, because that's how far along the curve we want to go. So if we multiply length by 0.9, this will be our from min value. Probably wouldn't hurt to add some smoothing to this as well. And now we should be able to use this to mix between our rotated position and our original position. So we'll do a mix with this as the factor. We're going to be mixing vectors. Any qualifying vertices are going to get vector B, and any that are behind our pivot point are going to just keep their original position. So let's pop that into there. And we should now get rotation only on the correct vertices. We could experiment with the values here. Maybe we could try this at 0.8. We need to keep these in sync. And I think rather than applying the smoothing here on this map range, if we were to put this result through a float curve instead, then we could probably tweak our values a little bit more precisely so we get just the result we want. I'm going to leave it there for now. So obviously we don't just want a fixed angle here, we want to have some variation over time. So if we drop down a scene time node and a noise texture, 1D noise will be plenty. We can drive the W of that noise via our seconds, this into our angle. But what we want to do first is just subtract 0.5 so that we get positive and negative values coming out of here. And we're also going to want to multiply this up a little bit, otherwise we're just going to get very small rotational values. So if we put this to something like 30, not 30, because strangely enough the input here is in degrees, but as soon as you add a connection, Blender treats this as radians, so we're going to need a much smaller value, probably something like 0.5 would have actually worked fine. Up a little bit for testing. Have a look. Well, it's working, but we're going to want to slow it down. Let's remove the detail from this noise and make the scale much smaller. Still probably a bit fast. And this will depend on the model that you're using and the scale of the caterpillar. So that's pretty good. And with that, I think we're going to call this done. Thanks ever so much for watching. I'll see you in the next one. Bye.